In this video, I'm going to solve one differential equation using three different common methods: the Laplace transform, the undetermined coefficients, and the Green's function. We have a toy model here, which is a linear second order non-homogeneous ordinary differential equation, and we have two initial conditions, non-zero initial conditions. So we have a non-homogeneous equation and two non-homogeneous initial conditions. Let's start the first one, the Laplace transform. As you know, in the Laplace transform technique, we take the Laplace transform of both sides of the equation. These terms are the Laplace transform of the second derivative of y, and the last one, f of s, is the Laplace transform of the y itself. Okay, and the second hand, the right hand side of the equation, we have the sine function, and this is the Laplace transform of the sine function. You can easily find the Laplace transform of the unknown function, and you have to decompose this huge term here, and we have three smaller terms, and I can easily find the inverse Laplace transform of these terms, and the final result of the equation is something like this. This is the Laplace transform approach. The second one is the undetermined coefficient method. In this one, first you have to solve the homogeneous form of the original equation, and then you can find a particular solution, and then add these two solutions together, and the combination of these two solutions is the final solution of the original equation. Okay, at the first step, I'm going to find the roots of the characteristic polynomial r squared plus 1 equals 0. So the roots are complex roots, and the general solution of the homogeneous equation equals c sub 1 sine function, and a combination of sine function and cosine function, c sub 2 cosine function. And then you must find a particular solution of the non-homogeneous equation using the undetermined coefficient technique. Here I will present a candidate for the particular solution, which is a combination of the sine function and the cosine function with two undetermined coefficients. Then substitute this candidate in the original equation, and you can find that the coefficient b equals 0, and the next one is negative 1 over 3, 1/3, and then you can compute the unknown coefficients using the initial conditions, and you will obtain exactly the same expression as the previous one. Alright, the third one is the Green's function approach. This approach has three main steps: step number 1, step number 2, and step number 3. At the first step, you have to compute the Green functions of the original differential equation. The Green's functions are the solutions of the original differential equation, in which the right-hand side is replaced by the Dirac's delta function. And also the boundary conditions are all equal to 0. So I have a non-homogeneous equation with homogeneous boundary conditions. It's obvious that the solution of this equation, which is called the Green's function, is independent of the function at the right-hand side, and is just dependent on the linear operator of the left-hand side of the equation. You can take the Laplace transform of both sides using these initial conditions, and we have this simple algebraic relation in the Laplace domain. So the Laplace transform of the Green function of this equation equals 1 over s squared plus 1. So you can easily take the inverse Laplace transform of this relation, and the Green function of that equation is the sine of t. This is the first step. The second one is to find the solution of the homogeneous form of that equation with non-homogeneous initial conditions or boundary conditions. In our case, the initial condition. So similar to the previous one, you have to solve the characteristic polynomial, and you have to find the roots, and then phi of t, which is the solution of this form of the equation, equals a times sine of t plus b times cosine of t. And then apply the boundary conditions or the initial conditions using these constraints here. A equals 1 and b equals 2. So a part of this final solution is the phi function, which equals the sine of t plus twice the cosine of t. The third step of the green function approach is to find another function, which is I here, and add this function to the phi. This is the form of the convolution integral. Here g is the green function, and this one is a non-homogeneous function in the right hand side of the original equation from 0 to t. This integral is straightforward. You can convert the product of two sine functions to the subtraction of two cosine functions, and this is the primitive function from 0 to t. After replacement of two limits of integration, this equation is the I in the integral. So add I and phi, and you obtain exactly the same result of two previous approaches.